every time you open your laptop, it really does feel like a black box, doesn't it? You hear all the jargon kernels, stacks, caches, and somehow the sheer complexity, it builds this sort of mythology, makes the computer feel almost mystical, hidden behind all these layers of arcane software.
And that's precisely why computing is often taught. Well, upside down, really. You get handed this beautiful glowing screen and someone tells you to write a loop before you even grasp what the machine is fundamentally doing.
Right.
But if we strip away all that ceremony, a computer isn't mysterious at all. It's actually a machine executing a physical argument. It's the modern face of a very old, very simple impulse to trap thought in matter.
That's the core idea for our deep dive today, isn't it? We're kind of pushing back against the notion that computing is inherently difficult.
Exactly.
Our mission, if you like, is to start at the simplest, most basic truth. We're literally going to build a computer using, well, basically dirt and rocks.
Oh, yeah. Dirt and rocks.
And from that very humble start, we're going to trace those ancient physical principles all the way up to the absolute physical limits of information storage, which incredibly takes us to black holes.
Because the core logic, the essence of it, hasn't aged a day. Whether it's silicon or soil, the mechanism is fundamentally just a dance of differences. This thing is not that thing made permanent.
Permanence.
That persistence, that lasting mark left by a decision, that's what we call state.
Okay, let's unpack this. Let's start with the lowest tech system imaginable. The dirt computer. You said a computer manipulates information according to rules.
Right.
And that information, it really doesn't care about its physical form. Could be voltage, beads on an abacus, or, rocks and holes.
So we have to start with the absolute fundamental unit, the bit. For you, listening, just imagine digging a fist-sized hole in the ground.
Okay, done. I've got one hole. Mentally, anyway.
Okay, good. That single hole can store one bit of information. An empty hole, let's say, that equals 0. You put a rock in the hole, that equals 1.
Simple enough.
This system stores exactly two possible states. It answers one single yes-no question. Is there a rock? Yes or no? It seems trivial, I know, but this basic decision presence or absence is the bedrock of all digital technology.
Okay, so one bit is one hole. Now we scale it up.
Really?
If you dig 7 more holes right next to it in a row,
Now you've got 8 bits, or what we call 1 byte of storage.
and just by arranging them physically like that, in a line, you've basically invented binary positional notation.
That's absolutely right. The value isn't just how many rocks you have, it's where the rocks are. The hole on the far right, that's the ones position.
Yeah.
Then the next one is 2, then 4, 8, and it keeps doubling up to 128 for the leftmost hole.
Right, so if I wanted to store the number 5, let's see, that's 4 plus 1. So I put rocks in the hole for the 4 position and the hole for the 1 position.
Perfect.
And if I want to store, say, 200, okay, that's 128 plus 64, it's 192. You need 8 more. So rocks in the 128, 64, and 8 positions.
Exactly. It's elegant, isn't it? It shows you right there how every single digital number, every piece of data is ultimately just a pattern. Presence and absence. Rocks and no rocks.
Okay, but just having a row of holes isn't very useful if you want, like, actual memory. We need structure.
We do. So let's make a grid. Maybe 8 rows, and each row has 8 of those holes.
Okay, 8 by 8, that's 64 holes total.
Which gives you 8 bytes of storage.
And this is where random access memory, RAM, comes in, right? I need a way to find the data I stored in, say, the 5th row.
That's addressing. You just number the rows or the byte locations, maybe 0 through 7. If you need the value stored in byte 5, you go directly to row 5 and you read the pattern of rocks in those 8 holes.
And the random access part means I can jump straight to row 5. I don't have to check rows 0, 1, 2, 3, and 4 first.
Precisely. You can access any location directly, randomly. That's the key to RAM speed.
Okay, storage sorted, dirt RAM. Now, how do we compute? We need something like an arithmetic logic unit. An ALU.
Yes, the ALU. Let's tackle addition. Because honestly, almost every complex mathematical operation, whether it's rendering graphics for a game or training an AI model, it boils down to just doing lots and lots of additions really, really fast.
Okay, let's try adding 5 plus 3 in binary dirt holes.
All right, so we set up the number 5, 0, 0, 0, 0, 0, 0, 1, 1 in one row of holes, and 3, 0, 0, 0, 0, 0, 0, 0, 0, 11 in another. Then we follow a simple bit-by-bit procedure, starting from the rightmost bit, the ones position, and we need to keep track of the carry.
The carry, right? That's like in grade school addition when you carry the 1.
Exactly like that. So position 0, 1 plus 1, that's 2, which in binary is 10. So the result for this position is 0, and we carry a 1.
Got it. 0 carry 1. Okay, next position, the 2's position. We have 0 plus 1 plus the carry from before.
Which is another one. So 0 plus 1 equals 2 again. Binary 10. So result is 0 carry 1.
Okay, position 2, the 4's position. We have 1 plus 0 plus the carry of 1. That's 0, 2 again. So 0 carry 1.
Still with me. Good. Finally, position 3, the 8's position. We have 0 plus the carry of 1. That just gives us 1.
And no more carry. The rest are zeros. So the result is 0, 0, 0, 0, 0, 0, 0, 0, which is 8.
Correct. 5 plus 3 equals 8. And what's really fascinating there is that the whole complexity of addition boils down to managing that single carry rock or bit.
And in this third computer, the human, me following your steps, I'm basically the processor, the thing executing the rules.
You are. You're implementing the formal rules of binary addition. There are actually 8 simple rules that cover all possibilities, like 0 plus 0 plus 0 plus 1 plus 0, 1 plus 1 plus 1, and so on. In your modern CPU, those 8 rules are physically built into tiny circuits called transistor gates.
Okay, so addition is one key operation.
Yeah.
But you mentioned logic in ALU. What about logic gates?
Yeah.
Like XOR, exclusive OR.
XOR, yes, very important. XOR is essentially a difference detector. Its output is 1 only if the 2 inputs are different.
So the XOR is 0. 1 XOR 1 is 0.
Also correct.
But 0 XOR 1 or 1 XOR 0, that gives you 1?
Exactly. It only signals when there's a difference.
And that's useful for more than just math, right? I remember something about error checking.
Absolutely. XOR is crucial for things like checksums and parity checks. If I send you a message, say a byte of data, and you have a copy of what I should have sent, you can XOR the byte you received with your known good copy bit by bit. If the result is all zeros, no locks, then the message arrived perfectly.
But if even one bit flipped during transmission,
then the XOR operation for that bit position will result in a 1, a rock. It tells you instantly that something changed and often where. It's fundamental for data integrity.
Okay, this is cool. We have storage, RAM, we have processing, ALU with addition and XOR.
Yeah.
But you said I was the control unit following the steps. How do we automate that? How does the computer know what operation to do next?
Now we formalize your role. We need an instruction register. Think of it as another special row of, say, 8 holes. But the pattern of rocks in these holes doesn't represent data. It represents a command.
An instruction code.
Exactly. For instance, maybe the pattern 00000000011 tells the computer perform an ADD operation. And 00000000100 might mean load data from a specific RAM address into a working register.
Okay, so we have codes for actions. Where do these instruction codes live?
We store sequences of these instructions one after another in a dedicated area of our holes called program memory.
So the program itself is just stored like data. Rocks and holes.
Yes. That's a key insight of the von Neumann architecture. Instructions and data are stored in the same memory space.
But how does it know which instruction to execute now?
You need one more piece. A special counter. Just another byte of storage, maybe, called the program counter, or PC. The PC simply stores the memory address of the next instruction that needs to be executed.
Ah, I see. So there's a cycle.
There is. It's called the fetch, decode, execute cycle. It's the heartbeat of almost every computer.
Let me guess. Fetch.counter. Read the address in the program counter. Go to that address in program memory and fetch the instruction code, the rock pattern.
Yep.
Decode. Figure out what command that rock pattern represents. Like, oh, it's 000000. That means ADD.
Right.
Execute. Perform the actual operation, maybe using the ALU, and then update the program counter to point to the next instruction in the sequence.
Precisely. You fetch, you decode, you execute, you increment the PC, and you repeat over and over incredibly fast.
So using just this set of RAM holes, ALU rules, instruction codes, program memory, program count, we can actually write a simple machine code program, like find the biggest of 3 numbers stored somewhere in our dirt ramp.
Absolutely. You'd use sequences of instructions like low number A, low number B, compare A and B, maybe a jump if greater instruction that changes the program counter, to skip ahead if A is bigger, store the bigger number somewhere, and so on.
It's all just patterns of rocks, controlling other patterns of rocks.
That's the essence of it. And the entire history of computing, really, from Charles Babbage's mechanical difference engine with its gears,
to the relays in the Harvard Mark I,
to the big hot vacuum tubes in NES,
and finally to the tiny transistors in modern CPUs,
has simply been about replacing that slow, error-prone human control unit and those clunky physical mechanisms with faster, smaller, and more reliable ways to represent and manipulate those bits. The fundamental logic, though, It hasn't changed one bit, pun intended.
And the scaling is just
Yeah.
mind-boggling. We started with 8 bytes in our little dirt patch. A modern PC might have, what, 32 gigabytes of RAM?
Or more. That's 32 billion bytes. To replicate that with our dirt computer, you'd need 256 billion holes. It would be a field of holes stretching for miles and miles.
Wow.
Yet a modern CPU, maybe it has 20 billion transistors, maybe 50 billion now. It's still doing that same core dance. Storing bits, adding bits, comparing bits, following instructions, encoded as patterns of on and off states.
Which really drives home that incredible idea you mentioned,
Yeah.
substrate independence.
Yes, it doesn't matter what holds the bit.
Whether you're writing in Python or C++ or whatever fancy language, eventually it all gets translated down through compilers, assemblers.
Right down to the machine code, the raw binary instructions, the patterns of rocks.
Every single program, no matter how complex, is ultimately just, as you said, a sculpted sequence of if this, then that.
That's probably the single most important lesson here. Computation doesn't care about the physical stuff it runs on. Rocks, gears, vacuum tubes, silicon transistors, maybe someday quantum states. The pattern and the logic are what matter. The medium just affects the speed, the cost, the size.
Okay, so we've established computation is substrate independent. The logic is universal. But building our dirt computer wasn't free, was it, when we dug that first hole?
Ah, yes. The physics.
It did work. We expended energy. We, disturbed the universe a tiny bit.
You committed a subtle violence against the universe. No, seriously, you performed work against physical potentials. You changed the configuration of matter, and that always has a cost. We had to invest energy to create the potential for storing a bit.
Can we quantify that? How much energy did our dirt bit actually cost?
We can estimate it. Let's say your fist-sized hole is roughly, 10 centimeters deep and maybe 10 across. The dirt you excavate has mass, maybe around 1.18 kilograms. Lifting that dirt out of the hole and moving it aside costs energy, primarily against gravity. You also create new surface area on the sides of the hole, which has a small surface energy cost. If you crunch the numbers, the total energy you invested just to create the empty hole, the container for the bit, is roughly 0.6 joules.
0.6 joules to make the zero state possible. And that energy is now stored where?
It's stored in the potential energy of that configuration. The hole represents a higher energy state for the soil system compared to flat ground. It's a strained configuration.
And why did we have to spend that energy? Is there a deeper principle?
There is. It connects beautifully to Noether's theorem from physics. The theorem basically says that for every continuous symmetry in the laws of physics, there's a corresponding conserved quantity.
Okay.
Well, flat ground has translational symmetry. You can move sideways and it looks the same. But when you dug the hole, you broke that symmetry. You created a special non-uniform spot.
Ah, I see. Breaking the symmetry requires...
It requires an input of energy, according to Noether's theorem, which relates spatial symmetry to momentum conservation and ultimately energy conservation in the whole process. That energy gets stored in the new configuration, the hole. Energy has to be conserved, always.
Okay, 0.6 joules invested. Now, what about the state difference? Putting the rock in the hole to make it a one-way.
Interestingly, when you place the rock in the hole, you're actually lowering the potential energy of the rock hole system slightly. The rock is more stable in the hole than sitting beside it. That energy difference, maybe around 0.098 joules for a typical rock, gets released.
Released is what?
Heat and sound, mostly. The thump when the rock lands. So in our specific dirt computer, the one-state rock and hole actually has slightly less potential energy stored in it than the zero-state empty hole.
That seems counterintuitive, but the key point is there's an energy difference between the states.
Yes, and more fundamentally, the act of changing the state, of making or erasing a bit, has an unavoidable thermodynamic cost. There's a minimum price the universe demands for irreversibly manipulating information.
And this is where the Landauer limit comes in.
Exactly. Rolf Landauer figured this out. Landauer's principle states that erasing one bit of information, which is a logically irreversible operation necessary for most computations.
Because you lose the previous state information.
Right. That erasure must dissipate a minimum amount of energy into the environment as heat. And that minimum energy is given by a simple formula. Mn equals kBT T ln2.
Okay, Kb is Boltzmann's constant, T is the absolute temperature, and ln2 is the natural logarithm of 2. What does that work out to?
At room temperature, say around 300 Kelvin, that minimum energy Mn is incredibly tiny. It's about 2.8 times 10 to the minus 21 joules. 2.8 zeptojoules.
10 to the minus 21. That's almost nothing. That's the absolute theoretical floor for the energy cost of computation.
For erasing a bit irreversibly at that temperature, yes. That's the thermodynamic ideal.
Okay, now let's compare. Our dirt bit costs about 0.6 joules just to create the possibility, and changing its state involved energy too. The Landauer limit is 1021 joules. That difference is astronomical.
It is. It's a factor of something like 10 to the power of 20, or maybe 10 to the 21. It's enormous.
Let me try to grasp that. It's like 100 million billion times less efficient. Our dirt bit compared to the absolute physical limit.
Something like that, yeah. It's a stark measure of how incredibly inefficient our macroscopic classical operations like dropping rocks or even flipping today's transistors are compared to the theoretical minimum dictated by thermodynamics. Modern transistors are much, much better than rocks, obviously, but they still operate millions or billions of times above the Landauer limit.
Wow, so information is deeply physical. Creating it, erasing it, it all has real energy costs, even if the theoretical limit is tiny.
Absolutely. And if information is physical, how permanent is it? Can it truly be destroyed? That takes us toward the ultimate limits.
Okay, so if we're storing information in matter using different states, what stops all matter, and thus all information, from just collapsing into some uniform, indistinguishable mush?
Ah, good question. That's where pillar of quantum mechanics comes in, the Pauli exclusion principle.
Named after Wolfgang Pauli. What does it say again?
It states that no two identical fermions, and fermions are the particles that make up matter, like electrons, protons, neutrons, can occupy the exact same quantum state at the same time in the same place.
Why is that so important for information?
Because it guarantees distinguishability and stability. If electrons could all collapse into the lowest energy state in an atom, atoms wouldn't have their shell structures, chemistry wouldn't work, and matter as we know it couldn't exist. Pauli's principle forces matter to occupy diverse states, to take up space, to be structured.
It forces complexity, which allows for different states to store information, are rocks and holes, or different electron energy levels.
Precisely. It underpins the very existence of stable, distinct states needed for memory.
And quantum mechanics offers another guarantee, doesn't it? About information not being destroyed.
Yes, unitarity. This is a fundamental principle stating that the evolution of a closed quantum system over time is described by a unitary operator. What that means, in essence, is that information is conserved.
So you can change it, you can scramble it, but you can't fundamentally delete it from the universe.
According to quantum mechanics, no. The information is always preserved within the total state of the system, even if it gets incredibly spread out or hidden.
Which leads us straight into the biggest puzzle where this seems to be violated: the black hole information paradox.
The ultimate cosmic test case? Yes. Here's the problem. You take something with a perfectly known quantum state pure information, and you throw it into a black hole.
Okay. Information goes in.
Then, over maybe trillions of years, Stephen Hawking showed that black holes evaporate. They emit radiation, now called Hawking radiation. But the radiation Hawking predicted seemed to be purely thermal random. It contained no details about what fell in.
So the pure state information that went in seems to just vanish, replaced by random heat.
Exactly. It looked like the black hole was truly destroying information, which would violate unitarity, a cornerstone of quantum mechanics. Big problem.
So what's the thinking now? Is information lost or not?
The overwhelming consensus among physicists today is that information is conserved. Unitarity holds. The information isn't lost.
So where does it go?
It must somehow be encoded in the outgoing Hawking radiation. Not in the obvious way, but in incredibly subtle, complex correlations between the seemingly random radiation particles. The information is highly scrambled, spread out across the entire evaporation process.
So the black hole acts like the universe's ultimate shredder or blender. It doesn't destroy the information, just makes it almost impossible to read.
That's a good analogy. The information gets thermalized and scrambled, but the underlying quantum description, we believe, remains unitary and complete. We just don't have the dictionary to unscramble it yet.
And speaking of the ultimate limits, there's the holographic principle. That relates to how much information can even fit in a region of space, right?
Yes. It's a mind-bending idea, partly inspired by black hole thermodynamics. It suggests that the maximum amount of information you can pack into a volume of space isn't proportional to the volume itself, as you might intuitively expect.
More space, more information.
You'd think so. But the holographic principle says the limit is proportional to the area of the surface that bounds the volume. like the information is written on the boundary, like a hologram.
That sounds completely
It
backwards.
does, but it comes from the Bekenstein-Hawking entropy formula for black holes, which states their entropy, a measure of information, is proportional to the area of their event horizon.
Can you give a sense of the scale? How much information could fit, according to this?
The numbers are staggering. Take a sphere just 1 meter in radius. If you could use every possible degree of freedom allowed by physics within that sphere, the theoretical maximum information capacity, according to holographic bound, is around 4.3 times 10 to the power of 70 bits.
10 to the 70. That's just, I can't even picture that number. That's vastly more than all the data on Earth, right?
So vastly more than the estimated number of atoms in our entire galaxy, maybe even the observable universe, depending on estimates. It's an astronomical amount of potential information density.
Okay, one last comparison then. We talked about the energy cost. Our dirt bit was terrible, 0.6 J-bit. Landauer limit at room temp, 1021 J-bit. How efficient is a black hole as a storage device, theoretically?
If you consider the energy locked up in a black hole via EMCT Furry relative to the information it can store, its Bekenstein-Hawking entropy, the theoretical energy cost per bit is astonishingly low. For a black hole with the mass of our sun, it works out to something like 10 to the minus 30 joules per bit.
10 to the minus 30, that's...
That makes the black hole about 1 billion times more energy efficient at storing information than even the room temperature Landauer limit suggests is possible for conventional irreversible computing.
So the universe allows for incredibly dense and efficient information storage, at least in these extreme objects. But getting it back out, that's the hard part.
That seems to be the cosmic bargain, yes.
So we've really gone on a journey here, from a simple hole in the dirt representing a single bit,
All the way to the event horizon of a black hole, the densest information storehouse we know of.
and the thread connecting them is that information is fundamentally physical. Creating it costs energy, its existence relies on principles like Pauli exclusion, and its fate seems governed by deep conservation laws like energy conservation via Noether and quantum unitarity.
The miracle of computation, then, isn't magic. It's just the power of applying very simple, repeatable operations, like checking for a rock or carrying a 1 at incredibly massive scales using faster and faster substrates.
Okay, so pulling it all together, what's the final provocative thought we can leave people with? Something connecting this finical nature of information back to computation itself.
Well, think about what we discussed. Black holes are incredibly good at mixing and scrambling information, making it hard to retrieve.
Right, the irreversible blender idea.
Now consider a famous problem in computer science, factoring large numbers. Multiplying 2 large prime numbers together is easy for a computer. That's like mixing information.
Okay, easy mixing.
But taking the resulting very large number and finding its original prime factors, that's exponentially hard for classical computers. That's the basis of most modern encryption. It's hard to unmix or unscramble that information.
I think I see where you're going.
So the provocative thought is this. Is the computational difficulty of problems like factoring the difficulty of unscrambling information actually a reflection of a fundamental thermodynamic principle?
Like the universe finds it easy to increase entropy, to mix things up, to scramble information like a black hole does.
Exactly. But reversing that process, unscrambling, reducing entropy locally, retrieving that specific original order, that requires significant work, exponential effort perhaps, just like thermodynamics dictates that creating order out of chaos is costly.
So maybe the reason breaking encryption is hard isn't just a quirk of mathematics, but it's tied to the fundamental physical laws governing energy, entropy, and the universe's tendency towards irreversible complexity.
It's a fascinating possibility, isn't it? That the limits of computation might ultimately be rooted not just in algorithms, but in the physics of information itself, reflected in everything from dirt holes to black holes. The universe is good at mixing, but it makes unmixing extraordinarily difficult.
A really stunning thought to end on. The ultimate difficulty of cracking a code might be written into the laws of the cosmos. Thanks for digging deep, quite literally, into the bit with us today.